Tell me when you want me to change slides.
Get back on the thingy, because it's thinking.
Yeah.
Shut the fuck up.
Alright. Hey guys, I know most of you. I'm Alistair, for those of you who don't know me. I'm an aspiring physicist. I want to go into astrophysics because space is really cool. Before I start, I have a small confession to make. I really wanted to make this as basic as possible. I was thinking to myself when I was making this that I wanted to teach it like I was teaching to my brother and sister, which means that a lot of the math has to be excised, but next slide. There's a really symmetrical beauty in physics, and a lot of it can't really be explained without math. And so there are going to be equations in here, and they're going to be, the only ones that I've included are the ones that are either so absolutely fundamental to the way that we perceive the universe that leaving them out would be like, I would be depriving you guys of something amazing. Or their forms they reflect symmetry. And symmetry is a word that comes up a lot, especially in really high level physics. But just some of the most basic forms of the equations appear in something like gravity, and then they appear again in electromagnetics, and then they appear yet again in like particle physics. And it's just really cool how all the forces of nature, I guess, keep appearing over and over again in all the different forms. And if I start rambling about too much into my math, my siblings have kind of gained the ability to just call me out and say, stop, too much math, put it in words I can understand. So please, if I start talking in words that are just like don't make any sense, shout at me, throw things, do whatever, bring me back on track. So we're going to be covering the four kind of basic areas of physics, and there's a whole bunch of subcategories, but most of them can be divided into this. Mechanics, which kind of, next slide. Yes, here we go. Mechanics deals with you, me, everything, the Earth, the sun, the stars. A lot of astrophysics is classical mechanics, so it's like gravity, forces, energy, and so they're far less than the speed of light, but far larger than an atom. Whereas relativistic mechanics, which is some really crazy stuff, and I love it, doesn't make any sense, but it deals with things that are 1% or more the speed of light, and then quantum, very, very small, much smaller than the size of an atom, and quantum field theory is really far out there. And my ability to understand them goes classical, relativistic, quantum, and I don't even include quantum field because that's too much. But quantum field is what they're doing at CERN with the Large Hadron Collider. Lots of really smart people work there, and it's great. So yes, the four fundamental forces in loosely descending order of my ability to understand them. Gravity, E&M, weak nuclear, strong nuclear. And then there's a reason this one's so far down there. Loosely descending order of ability to understand. These can all be explained with high-level particle physics, and I don't want to talk about that. I put Ceiling Cat because he's the best explanation I can think of right now. Yeah, mechanics. As I said, it governs everything around us. We're going to talk about forces, gravity, energy, and simple harmonic motion because it's relevant. Next. So, forces, they come in a lot of forms, and this equation is important. I'm going to write it up there because I'm going to write it over here. F equals ma. Most of you have probably seen this equation before. I don't know how many physics, or how many of you have even dabbled in physics. It's force equals mass times acceleration. So the mass of an object in kilograms times its acceleration in meters per second, which is the increase in velocity every second. That is, we use this one a lot. And forces come up in torques. Torques are rotation, and there's a lot of relevance between like straight line movement and rotational. So you've got the equation, to erase this.
Yeah, go nuts.
Just don't erase the Dalek.
Not
Right
near
hand
there.
side. Okay.
So you've got the equation v is equal to v0 plus at, which is velocity is equal to the initial velocity, so your starting speed, plus acceleration times the time that you do all of this for. And in angular rotation, which is like, say I'm spinning something, you hand me my earphone. That's actually a really cool experiment that was done that proves why these always get tangled when you put them in your pocket. But the Ig Nobel prizes, which are like the Nobels except for every day not quite as exciting as a particle physics. So when I spin this, and I'm going to just half because it's go everywhere. When I spin this, there is a speed that this is moving, and at the very top, so right here, as it moves around, there's a velocity that goes like this, and then you have the angular velocity, which is best expressed in polar coordinates, which I never had explained to me. But it basically says that the speed that it's moving around is proportional to the speed that it's moving up here, in terms of degrees or radians per second. Radians are metric. And that equation looks like omega equals omega squared plus alpha times t. They're basically the same, except one of them deals with polar coordinates and one of them deals with ordinary straight line coordinates. Gravity. That's the next slide. Okay, yeah, gravity. That equation up there is everything. Like, it's the reason that we exist today, because without gravity, we wouldn't have the force that pulls everything towards, or pulls the sun into its constituent parts, pulls the planets into their constituent parts. And it basically goes, I need to write this one down as well. Force of gravity equal to g, which is a constant, very small, like 6.67 times 10 to the negative 11, which means basically 1 over 6 times 10 to the 11th, minuscule, which is why it only affects things that are so huge. Gravity, which is just, it's Newton's constant times the mass of one object times the mass of another object divided by the distance between the squares. Also negative, because in the real world there's no such thing as negative mass, which means that you can't have two objects repelling each other because of gravity. The negative means that they always move towards each other, they always accelerate towards each other. And because they're both forces, it's possible to set them equal to each other. So mass times acceleration equal to dm and r squared. This mass is u, this mass is u, so it's the force that you exert on the Earth, which is also the force that the Earth exerts on you, but they cancel, so it doesn't matter. And this is the acceleration due to gravity. So when I jump, the speed that I come back down to the Earth at is defined by this. This mass is the mass of the Earth, which is enormous and significantly larger than mine, I should hope. And then energy, which is mgh. H is actually change in height, and so when I jumped, my height went up by like we generously call it half a meter. That is significantly smaller than the radius of the Earth, because this r is the distance from my center of mass, somewhere around my belly button, higher than most railings, which is dangerous, all the way down to the core of the Earth, where the center of mass is located. And but when I jump, I add half a meter to that. The distance in meters from me to the center of the Earth is like, yeah, 600,000, something like that. So it doesn't matter, and which is the reason that I wrote this, sort of, is because on Earth, that's the equation that we use because there's not really anything that can significantly change the distance between me and the center of the Earth. So the r plus, so it's like 600,000 plus, it doesn't matter. So that equation is going to come up later in EM. So I'm going to write that in here. U is, by the way, energy, which describes, just writing this down. Energy is force exerted over a distance. So if I were to pull this chair all the way over here, I have to accelerate it, and the amount that I accelerated is equal to the work that was done. And energy also comes in a lot of forms, like chemical, kinetic, and potential. Potential is the one that we deal with the most, and the one that we care about the most, because all energy is derived from potential energy. So all the stuff in like chemistry students that they do deals with the potential energy stored inside the chemical bonds. Also physicists do is also, or astrophysicists do is deals with like potential energy stored in chemical bonds. I don't like chemistry. So when we send a rocket into space, we're releasing the potential energy inside the chemical bonds, and using that to push the rocket straight upwards, accelerating it, increasing its potential energy through an expenditure of kinetic energy. And energy and mass must be conserved, mass energy. So the entire amount of mass in the universe is the same as it was at the very beginning. And while mass and energy are interchangeable, E equals mc squared, which I will slide on later, the whole total sum of that is the same as it has been in the since the beginning of the universe, and it's slowly moving towards energy because of entropy, which will eventually lead to heat of the universe probably. So yes, everything that you do day in, day out is leading to the heat of the universe. Good job, guys. Simple harmonic motion. When I was swinging that, I was not only dealing with angular rotation, but also emulating simple harmonic motion. Because as you can see, simple harmonic motion is anything that moves back and forth regularly. So springs, which are important. Springs, right. So springs are, as an example there, and when you pull it down, it exerts a force back towards the center, and then when you push it forward, it also exerts a force back to the center. So it's always trying to come to an equilibrium. But its motion in a perfect spring, which would continue going up and down, and never stop once you put energy into it, emulates this circle, which was the same thing that was happening when I was spinning the airplane. Another interesting example is if you were to dig a hole from here all the way to whatever's on the other side of the Earth, somewhere in the mid-Atlantic, don't do that. Try and make it come up on land. So if you dig this hole all the way down, and it didn't collapse in on itself and you didn't die from the heat, if you drop something down there, it would take around 42 minutes to go down, and then around 42 minutes to come back. And in doing so, it would look a lot like this, which is where simple harmonic motion gravity. And then sound, the waves that I am emitting from my mouth when I'm communicating with you guys, are also, well, if I were to be able to produce perfect pitch, which I'm not, will look like this. And if you see that, it's the same. The harmonic motion is inescapable. You deal with it all the time. Probably don't care about it so much. Not what I think about when I'm listening to music. Some of you might, that's cool. And then rotational kinematics, pendulums are like half of that circle. So it goes like this, this, and its speed, when you measure it, is similar to the speed of, or the acceleration of the spring. And the speed here is equal to the speed here, or in math terms, is yeah, let's do that. Alright, so negative kx.
And this is kinetic energy, or?
K is the spring constant. And equal to okay. So you got force, which hey, look at that. Force is equal to negative kx squared. So x being the distance that you offset it from the center. So you got your spring. Amazing at drawing springs. And when you stretch it, wow.
Beautiful.
When you stretch it, it's going to exert a force that wants to come back. It wants to go back like this. And why the negative is there? Same reason negative in this gravity, because it's always trying to come towards the center. And so if you compress this spring, as far as I know, there's no perfect springs that allow you to both stretch and compress them, but I could be wrong. So, this one will also exert a force outwards. And when you graph something, you get some really interesting, when you graph the motion of that, it's a sine curve, which was that thing that I mentioned before. Okay, so I promised myself when I was tutoring my siblings in kinematics that I would never teach physics without calculus again. Yet here I am trying to do it. Are there any calculus students here? Anyone who's taking calculus?
About 10%.
Fair enough.
Yeah, not 10 to 12.
High school counts, yeah.
Yeah, usual calculus should be funny for that.
Yeah, usual calculus. So, you remember derivatives and integrals?
I remember 10 yeah.
Close enough.
Did you honestly on that exam?
Yeah. So, when you graph that motion, you get a sine curve. And this is the position. And then when you take the derivative of this, which will give you when you take the derivative of this, you get cosine function, which is the velocity. And then when you take the derivative again, another negative sign function, which is the acceleration. And you guys are taking calculus. You get similar effects with the position, velocity, and acceleration functions of just straight line motion. So if you were to draw lines of the car's position as it went from like here to Sydney, and then you took the derivative of that. Sorry, like these are all integrals, not derivatives. Yeah, because you're taking the area underneath it. So you take the area underneath this curve of a car driving from here to Sydney. We'll call it a triangle. Take 1/2 base on type. That will give you the average velocity. And And then if that car was traveling, if the velocity was steadily increasing, so by the time that you got to Sydney, you were traveling like 200 kilometers an hour. Don't do that.
Sounds like my uncle.
You can take the area under that curve and give you acceleration. So, in a similar fashion, taking the graph of this sine function for the position, and then you take the integral of that and getting the cosine, and then getting the sine. Again, you can get all the graphs, and they all look basically the same, except they're just offset by pi over 2. Great. Still further symmetry. So you can see how simple amount of motion, when you take the derivatives and integrals of each function, they map basically directly onto that from the both rotational, which makes sense because this is the same sort of thing, and onto the velocity, or onto the car traveling speed, straight line motion. Right, next. Electricity and magnetism. Okay, now we're moving into the stuff that I will. Now we'll be moving into stuff that we're actually covering in this class right now, and I just have my lab on it. So forgive me if I get some into
Okay, honey, we're here for you.
Okay, electricity deals with point charges. So when I talk about point charges, I'm meaning basically infinitely small massless point that carries some charge. And then electric fields are, you've got a whole bunch of point charges over here. All of these are positive. And then over here you've got a whole bunch of negative ones. And opposites attract, both in terms of electricity, magnetism, and people, strictly. You're going to get all positive forces, all positive charges are going to move in the direction of the electric field, which is a lot of physicists gets really mad about this, because whoever invented it, and I have no idea who, did a terrible job, because the base charge is an electron. That's what we deal with the most. There's no free-floating positive charge. All protons are kind of found on the nucleus. So most of the problems that physicists deal with electrons, and electrons do not move in the direction of the electric field. That'd be like saying the normal way of dealing with everything like gravity. So if I were to drop this pen, its ordinary motion would be not to go to the ground, but would be to straight up go to the sky and leave and accelerate forever. This is what physicists deal with. It's unintuitive. Whoever invented this notation should be taken back and shot.
They didn't know about the electron when that was invented, though.
Yes, but they should have. It wasn't a highly developed field at that point, and I am of the opinion that it could have been changed before it got written into all the textbooks that get so many college students. Those electric field circuits are deserving of their own talk. I mentioned this later. Alright, yeah, just go on. So yeah, electricity deals primarily with charges, positive and negative, and they all kind of, remember when I drew that electric field up there, I shouldn't have erased it. All charges move along these field lines. So all positive charges will follow these directions. So if you put a positive charge right here, it would travel up and away like that. Or if you put one here, it would go there. And somewhere over here, there's a point where this positive charge repels it more than this one attracts. So it will go away forever. Electric fields are created by motionless charges. Charges in motion create magnetism through some really cool effects. And electric current is produced by these charges, electrons for the most part, in motion. Next. That equation right there, F equals Q1, Q2 over R squared, is where I first began to realize just how cool physics was. Because it is gravity, but dealing with an entirely different subject, an entire other force of nature, but it looks exactly the same. So you got force, K, which is some constant, it's the opposite end of the scale. G is really, really small. K is enormous. It's like times 10 to the 9th. It's like speed of light big. Q1, Q2, and the absolute values are there are because you're basically trying to emulate this equation. You want to get just the charges, which are equivalent to mass, and then you want to calculate the force they exert on each other. However, unlike, I was about to say real life, but unlike Earth and mass, you can have negative charge, which means that things can repel each other. So you get positive charge and negative charge that are going to go towards each other. You get a positive charge and positive charge that are going to go away. And then all over R squared again. So same here. The really convenient thing about electricity is that, at least to me, I always think of it like mechanics. So you've got this electric field is equal to force over a charge. Charges can be thought of like mass, except that they can be negative. So if you rearrange that equation just by multiplying both sides by the q, you get F equals E Q. F equals M A. Sorry, some easy as another similar form. And then potential difference. Actually, we'll look at electric potential energy first. U E equal to Q times V. There you go. And if you look at the equation just above that, which is potential difference, you get V equal to the average electric field. So the electric field can change over a variety of places if you have more densely clustered charges or less densely clustered charges, times distance. If you plug this into here, so you take this voltage V here and replace it with E times E, U E equal to Q mass times E, mass times acceleration, so A times D. Sorry, G H D. Yeah, QED. Never noticed that. Same form. You just have to know which things to replace with the others. And so whenever I'm dealing with like point charge problems, I immediately substitute every single number they give me, every single variable they give me with its mechanics analog, because it's a lot easier to think of stuff in terms that I can actually picture in my head, because nobody can picture an electron. It's probability curve. Good luck picturing one of those. Good luck holding one of those. Yes, circuits. Huge. Like, they affect everything. These lights, that computer, the way that everything in this room was dealt with by circuits. But they're further mechanics analogs, and it's springs and fluids. Fluids, you can think of an electric current like water flowing through a pipe. As in, so the electrons flowing through it, the negative charge, which are moving opposite to the way they should be, are flowing just like water in a pipe. And so you get a lot of equations that deal with the way that this pipe of electrons, speed of electrons changes, the way that electrons will move towards areas, low areas in the ground or low areas of potential difference. And then capacitors and resistors behave a lot like springs. And these next slides look really bad, but I promise they're not as bad as they look. So you got some equations here, and you have some more equations down there. And the only thing that I want you to look at is the way that they look. So you want to compare these two, and you want to compare these two. They look exactly the same. This spring, and this is
Resistance.
this is resistance, this is capacitance. So when you look at the conduciveness of a spring, which is basically how willing it is to let you like stretch it or compress it, and then you put them all in series. So you see that over there? There's resistors in series. You can think of springs in series as basically the same. This is a spring square, 1, 2. And this is K, K, K. I mentioned spring constant earlier, and how much it prevented you from stretching it or compressing it. So when you look at the resistance, when you look at the capacitance, it resembles the spring constant. And then when you take the conduciveness of the spring, so how willing it is to let you stretch it, you get the resistance. And then if you go to the next slide, it's the reverse. And I found this was another one of those mind exploding moments in physics where I realized springs in series and I didn't explain parallelism, I'm so sorry. Parallel is when you got a bunch of springs or resistors, I suppose, like so. So there's distributing the load equally among them. So when you pull up on this, like this, these springs are all going to take equal amounts of weight. And then, so when you stretch this in series, also going to take equal amounts of weight. But the way that they behave, as in the way each individual spring contributes to the resistance or the conduciveness, is governed by these equations, which is the same way that the resistance, as in how difficult it is for charge to pass through the pipe, and capacitors, how easy it is to store this energy. And they behave exactly the same, despite being entirely different fields. More universal symmetry. Alright, next. Magnets. How do they work? Magnets are a really fun topic. And by fun, I mean make me want to pull my teeth out. When you're dealing with magnets, you can have two sorts of magnetic fields. Magnetic fields created by permanent magnets, which are like the sort of stuff that you used to play with when you were a kid and your dad told you to keep away from the hard drive or he'd take you out and beat your ass. That's me.
Oh no, that was a big true one.
That's pretty much ever.
Yeah, and so those are like so-called permanent magnets, as in they create their own electric field that looks like that, which is, I don't know, if you've ever seen the Metallica album, Coffin, it's also a magnetic field line, and that is created with iron filings, and that's a demonstration I wish I had. Unfortunately, I don't. I'm sorry. But yeah, when you put a magnet on a plate, and surround with iron filings, these iron filings will line up with the direction of the magnetic field, which makes it somewhat easier to picture in your head, except it's only in 2 dimensions and magnets operate in 3. One easy, I'll wait until I get to the next one. And then there's another way of creating magnetic fields, which is with electricity. And if you go to the next slide, electromagnets. Electricity and magnetism, if you've noticed, I've been referring to them basically as the same word in this whole talk, and that's for a reason. Because electricity and magnetism are the same thing. Maxwell, through a series of extremely beautiful and rather complicated equations, basically said that electricity and magnetism are the same thing, except electricity is operating in one axis, so like the up and down, and magnetism is operating in the next one. And the way that he came to this conclusion, well, he didn't come to this conclusion, like, basically, relativity basically, magnets are relativistic electrons. They are, when you're looking at the flow of electrons, they're moving at almost relativistic speeds. And in doing so, they increase your mass because as you go faster, your mass increases. And this creates an imbalance of charge, which is attempted to be corrected, or the effects of this are seen in the magnetic field. And I discovered this one this year, probably about 4 weeks ago, in Paul's lecture, and my head, I didn't even listen to the rest of the lecture. I was like, damn. For a good like 30 minutes. I was just sitting there in class like, what happened? Next.
Not the only one.
These are Maxwell's equations. And again, I'm sorry, this is very complicated. I can try and walk you through them, or I can just leave you to bask in their glory. Would you like me to try and walk you through them?
Maybe at the end if we have time.
Alright, sure. So relativity. This is like key. Okay, fine. There's a lot of things that's important that I talk about. This is probably one of the most important things because more so than electricity, magnetism, more so than even some of the most basic understanding of forces, this has changed how we look at the universe. Because with gravity, we always knew that if we drop something, it'll fall. With magnets and with electromagnetism, we've been able to exploit them, but they haven't really changed how we look at time. And time is the way that we perceive the universe. And special relativity explains why, if I were to go to Alpha Centauri at a quarter of the speed of light, I would be, and then come back, I would be younger than my brother. And my brother's like 3 years younger than me. I'm not sure how he would react to that. And the best way that I can demonstrate this, or kind of explain this one, is that, so imagine you've got an enormous clock behind you. And every 1 second, this clock gives off a flash of light. And this flash of light has the time written on it. And so you've got, so here's the clock. And here is, so, 1, 2, 3, 4. And let's say you go chasing after one of these. Because light is the fastest thing in the universe, there's no way that you'll ever be able to catch up to that 1 second. Nor even this 4 seconds if you leave after it. But if you were to go fast enough, you would be able to slow the distance, or slow the rate that the distance between the two of you would increase. So let's say that I'm traveling at a quarter of the speed of light, and I leave at the same time, just 1 second. Ordinarily, after 1 second, it would be like 800 billion kilometers away from me. But if I leave at a quarter of the speed of light, it's 1/4 that. And so by the time that I reach here, it's 4 seconds past. If I were to be able to exceed the speed of light, I would be able to catch back up to this 1 second. And then I'd be able to go beyond that. Which would mean that I would be looking at something that happened before I left. And if you were able to do this for an extended period of time, you would be able to go back to before the clock was in existence, before the universe was in existence, which is one of the reasons that it's impossible. Another good analogy for it is like, say you guys have been driving on a highway, and there's a car that passes you. Let's say that car is traveling at the speed of light. Just
sounds like my uncle.
So the atmosphere is on fire and we're all dead. Go on.
Yes. This car is traveling at the speed of light. It's only ever going to get farther away from you because it's traveling at a higher velocity than you. distance between the two of you is only going to increase. If you're able to go the speed of light, this distance would remain the same forever, but you would never be able to get back up to this car. If you're able to exceed the speed of light, you would be able to match the car and then exceed it. And this, we'll call this car like an event. As in, something happened when this car left, and because everything in the universe is governed by the speed of light, anything in front of that, that event hasn't happened yet. So if I'm talking about something all the way across the universe, actually even just the other side of the galaxy will do, and the star explodes over there. All the way over here, let's say that star is 200 light years away, and that star goes supernova. For 200 years, that hasn't happened yet. As in, it is physically impossible for me to do anything about that star exploding, or even react to it, because there is no way for me to know about that. And this is another key thing to information theory, which I don't understand, so I'm not going to talk about it. And that is the basis for special relativity, the fact that traveling close to the speed of light slows the pace at which events happen, because you're traveling so close to those events. Are there any questions? It took me ages to get this. I don't even get this properly. Yes.
With something like gravity, does that mean that the law of gravity, for instance, would still be in effect? Like, if we were some way able to measure the gravitational impact of the star 200 light years away, like, presuming we could see this in really, really tiny impact, would it still be affecting us with its gravitational pull for 200 years?
Yes, it would. And as I state, or as this part of the slide explains, that's how we know gravity waves exist. Even before we were able to observe them, even before the prediction of gravitrons, which are a fun word, even more difficult to find than Higgs boson. But we know that they exist because because everything in the universe is governed by the speed of light. If somehow that star were to explode and its gravity were to stop affecting us, we would be able to know the star was going to explode before it happened. As in, we would be able to go to the star and stop it from exploding because its gravity stopped affecting us. Gravity waves must obey the speed of light because otherwise information would be able to travel faster. Yes? No? Is that?
Well, I mean,
Is this something then that we have actually tested at to see that yes, gravity is obeying the speed of light, or would it just really screw with all of our equations if it didn't?
1 moment.
I'll wait till
Okay. Funny you should ask that, because about a month ago, we actually did receive the first evidence of gravity waves. But before that, we were in that position. It's like, all right, we're going to work on the assumption that these things exist, and if not, we're screwed. But we'll go with it anyway. And so we've received evidence of gravity waves. They have not been peer reviewed, so we are not 100% certain. But yes, for a long time we were just running that phase. Next.
With the theoretical wormholes and whatnot, where you'll be able to travel to a space faster than light outside of that wormhole, would that mean if you observed an event from that point and then travelled in a wormhole to a point further away where light hasn't reached it yet, has that event happened even though you've seen it?
Or does the event travel through the wormhole with you? And that's really just whack things up.
This is a bit beyond
Traditional
comprehension.
I
mean,
excellent
there's
question.
no one who really would know the answer.
Yeah, that's an excellent question. I'm sorry I'm not fully able to explain. I don't
If you
fully
were.
know my... If I were able to explain, yeah, there you go. I'll tell you what. If I am able to explain it, after I've made billions of dollars, I'll tell you.
You won't interact with
Alright, special relativity, which was what I spent probably 5 minutes explaining there, deals with just light, as in how it behaves in a vacuum without we physicists really like frictionless, fabulous, spherical vacuums. There's an old joke, and it's like, farmer's having problems with his chickens, and he goes to a chemist, a biologist, and the physicist to figure out what the problem with the chickens is. The chemist says, oh, it could be something with the way that the stomach acids in the chicken are working. The biologist says, oh, it could have a disease. And the physicist says, oh, we've come up with a solution, but it only works for spherical chickens in a vacuum. We only deal with perfect spheres, perfect vacuums, which makes applying physics to real life a little difficult.
None of the experiments.
Yeah.
Yeah, something like that. There's no way to perfectly replicate something on paper because there's always going to be external factors, minute gravitational shifts, air, people.
And sometimes the universe is just fucking with you.
And most
Yeah,
of it
but
has
actually-
incredibly high relationship standards.
Yeah, the Lorentz constant, this one is fairly easy to explain. You can just replace all of these numbers with A's and X's and Y's. It doesn't matter. It doesn't change it, except for that C. Yeah, that C is speed of light. And this Lorentz constant explains why we can't go faster than the speed of light. And it makes me, a lot of physicists, and a lot of science fiction fans really, really sad. Because this beta, here, equal to velocity squared over the speed of light squared. And so this equation governs how we perceive things. Not good. Okay. This is Lorentz transformation, which means that when you're dealing with something that's traveling loosely the speed of light, or around the speed of light, things that happen in the y direction stay the same, things that happen in the z direction stay the same, so up and down, in and out are fine, they stay the same. But when you're dealing with something that's moving across your field of vision, it gets modified by this constant. And this velocity is either your velocity or the object's velocity, how fast it's traveling. And so, if this number were to become 1, so if your velocity was equal to the speed of light, you would get 1 minus 1 under 1 equal to 1 over 0.
Oh, so
And
that's
then
what
the universe
math
ends.
becomes.
Yes,
That's the
and
math
then the
becomes
universe ends.
infinite.
Yes. This is why we can't travel faster than light. And it sucks.
Insane medium.
Can I just pause you for a second?
Like, it's faster than light in a medium.
Yes.
Everybody grab
That is
your
the fine difference. I neglected to mention. Neglected to mention that this value of speed of light, is the
Guys
value
are
of
animals.
light in a vacuum, which is the
I
fastest
thought
medium
bring
in
us
which
to
light travels. Light has many things to do. Travels faster in space with fewer things in its way. I travel faster in air than I do in water. And light also travels faster in air than it does in water. And it also travels faster in a vacuum than it does in air, than in water, than in some material that physicists in California did.
I think that was a very cool helium, in a very weird bosonic matter type thing.
I would be
Like
quite
that is one that was made with salt.
Yeah, so physicists have managed to slow down the speed of light by sending light through something like a hyperdense, super cool helium material. Which means, and I believe they eventually managed to bring it to a stop, which doesn't allow us to go faster than the speed of light in a vacuum. So all of these things that I've been saying are the speed of light in a vacuum. And so yes, I can travel faster than light, and I'm doing so right now, because this light is trapped in the super cool helium. I would not want to travel through the super cool helium.
Yeah, but if the light stopped, then wouldn't the medium just permanently store any and all light directed at it?
Yes.
So it
Maybe
would
leave some for someone else.
contain an infinite amount of light if you just kept shining a torch at it. Or it would. And you'd have no way to retrieve your energy.
The energy will heat up the material to the point where it would no longer trap it like that.
That would work. Okay. No, that makes sense.
Yes.
That makes a lot more sense.
Alright,
Otherwise,
that's
I'm
all
like,
I have to say on general relativity.
disturbing implications.
You could use it as invisible cream. Put it on your leg and hold your light.
That's, no, there's another word for that, that's,
Hypothermia?
Yeah. Anything badly?
negative, things with a negative index of refraction. Optics was one of the things that I was going to talk about, or considering talking about, but, yes. Optics govern how light reacts in different mediums, and, we have actually created something with a negative index of refraction, which would make you theoretically invisible if you were aware. Fabulous. Next. Alright, general relativity. So we dealt with special relativity, which deals with light in a vacuum with no gravity or anything else affecting it. This is the real world. Have all of you guys heard the analogy of Earth or the sun, or the universe is an enormous tarp, and you put a sun in it like a bowling ball, and it bends it, and that affects the way that, like, objects around it react, including light. Yes? Have you guys encountered this analogy before? Okay, so imagine the universe is an enormous tarp. And you put a bowling ball onto the tarp. And then you drop like a golf ball next to it. What's going to happen in the golf ball?
And roll towards the bowling ball.
Yes. We'll roll towards the bowling ball until it comes and sits in the area of lowest potential, which is potential energy. I know a lot, guys. And that is the most common analogy for how the universe works, and everything, not even light, is exempt from moving along the path of this bowling ball. And so when you shine a flashlight past it, these little dots of light that go by it are going to sink. They're going to follow this path, and it's going to be pulled towards the earth, and then it's going to move away. And general relativity deals with how this governs how you perceive the universe. Next. These are some really cool pictures of what happens when light does behave like this. So this is a simulated picture of a black hole, and it is 600 kilometers away from us. And it's sitting in the middle of the night sky, affecting how we see the Milky Way. And remember how we were talking about how light refracts when you send it through different mediums? Gravity does the same thing. And if you ever, I actually happen to have a glass with me. And so, have you ever put a pencil into a glass of water and you notice how it changes? Have you ever looked at the bottom of the glass of water? Like, looked down through the glass and seen how it warps the table or your hand underneath it? Black holes do the same thing to light, except instead of a different medium, it's warping like you. It's warping everything. It's great. Yeah, by the way, if this actually happened, we would only be alive for like a fraction of a second. So we don't want a black hole 600 kilometers away from us.
How rapidly does that destroy our atmosphere?
Yeah, but it'd be pretty cool.
Yeah, actually, to be fair, you could have like a micro black hole, which wouldn't do anything. But I'm talking like a stellar black hole. Learned something else really cool about black holes, but can wait until I've done it yet. This is a timeline of the universe, and it's general relativity states that we should see gravity waves, that we should see how gravity has been traveling over time and affecting things. And this thing over here is the cosmic microwave background, and that's kind of the basis for everything that we know about the beginning of the universe. That is the universe at 380,000 years, but on it we should see patterns of how the gravity of the early universe has expanded over the rest of the universe. Are you getting lost in my own thoughts? Alright, now for this. there's a few problems with relativity. Don't worry, I'll come back to the equals empty squared, but I'm not giving up yet. It's just, there's a few problems with relativity, namely that if our own Brian Schmidt won a Nobel Prize recently. I think it was recently, I don't know how many years ago it was. Proving that the universe is expanding. And we kind of expected the universe.
Expansion is accelerating.
And so, I actually thought of a really cool analogy about, like, how to explain this last night. So, imagine you're blowing up a balloon. And as you blow up the balloon, you run out of breath, and the balloon's full. And then, if you were to let the balloon go out of your mouth, it would collapse it back in on itself. That is what we expected to happen with the Big Bang. There was a huge, enormous output of energy at the beginning of the universe, and it was blowing up the universe like a balloon. And eventually, over time, we expected gravity to kind of slow that expansion down as you ran out of breath, and eventually stop, and bring it all back into a big crunch. What Brian Schmidt discovered is the universe is not doing that. So you're out of breath, and the balloon continues to expand, and expand, and expand, fill the room, you're suffocating. And nobody knows why. And congratulations, you're now all experts on dark energy, because that's all anyone knows about it.
Yay!
Yes. And it also fails to explain why 90% of the universe is missing. Because we can tell mostly from the rotation of various galaxies, using like redshift. I'll explain redshift and blueshift in a moment. Through like looking at the stars around us and how the galaxy is rotating, we're able to calculate through use of I erased this equation, angular momentum and angular rotation, that they're traveling at a certain speed, and thus they should have a certain mass. And the whole galaxy is rotating at a certain speed, and thus the whole galaxy should have a certain mass. And we're able to extrapolate the number of stars that we have in the galaxy, and then we're able to extrapolate the amount of mass that the galaxy has, and there is a big difference. And we don't know where it comes from. And relativity tells us that the universe is expanding and the expansion is accelerating. And relativity also tells us that there's a whole bunch of mass in the universe, and there's a whole bunch more mass that we can't see, and it doesn't tell us why. And that's one of the main problems with general relativity. And then it also can't be reconciled with sort of quantum mechanics, because at the very beginning of the universe, everything here, like the whole universe, was really small. And remember in the very second slide when I said that classical mechanics and relativity deals with things that are traveling, that are really big and really fast. Yes?
Mm-hmm.
Well, the universe was hugely massive and very, 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 very small. And around 10 to the negative 30 seconds, so 0.032 zeros later, 1 seconds into the universe, relativity breaks down because it can't deal with things that small. It can only deal with things that are really big and growing really fast. And the universe was really small and really fast. But it was also really massive. And we don't know how or why. And that's where the theory of everything comes in, which doesn't exist yet. Maybe one of you guys will find it. Maybe I'll find it. That'd be great. Make lots of money. But the theory of everything is supposed to unify general relativity and quantum mechanics so we can explain what happened at this point in time. Because before that, it's all just hand waving and guessing, and kind of like what happened before we knew gravity waves. Alright, go back. This equation is probably one of the most famous equations in all of physics. All the world, even. It's got a history, it's got a story. The people involved are actually, in some cases, less important than the equation itself. And I'll go ahead and break it down. Energy, which is the same stuff that we're dealing with here. Same stuff here, chemistry, rocket ships, getting out of bed in the morning.
Oh, coffee.
All that energy can be expressed as mass of an object, in kilograms, times the speed of light squared in meters per second. And as I mentioned, the speed of light is really big. It's something like 8.99, I can make long what I want, times 10 to the 9.
Isn't it 2.99?
Oh, yeah, sorry.
2.99.
Where did I get 8.99 from?
245.
Too many compounds. Yeah. Times 10 to the 8 meters per second. And then you square that, so you put another 2 up here, which brings you to 10 to the 16. Let me just explain how big this is for a moment.
Just quickly, what is it that you square it?
That is all.
Yeah, the derivation is,
It involves a larger, more complicated equation that has momentum.
Okay, now that makes sense.
yeah, there's a lot going on here, and I'm afraid I'm not intimately familiar with the derivation. Later, maybe, but, and then later in my life, I may be more familiar with it, but right now I know the equation, and I know what it means, and I know how to use it, but I don't know how we got there. And so 10 to the 16 is like, imagine 1 second, it just happened, cool. Now imagine 10 seconds, it happened probably since the beginning, it happened 10 seconds ago. And then 100 seconds has happened several times since the beginning of the talk. And then 1,000 seconds probably happened, that's about 30 minutes. So actually that might have been close to the beginning of the talk. 10,000 seconds is 2 and a bit days. 100,000 seconds is a couple months. And we're just gonna scale all the way up to, I don't know, a billion seconds. That's 33 and a bit years. And so we just went from 10 to the 1, sorry, 10 to 0, all the way to 10 to the 6. You've got almost, you got like 2 and 2/3 of that in this. So that's the difference between 1 second and 33 years times, actually it's not even times, it's exponentiated. It's big, it's a lot, and that's a lot of energy. You can do a whole bunch with it. And that's why, despite the fact that Einstein was a pacifist, that's why the atomic bombs were so effective, because they took like just fractions of a kilogram, like itty bitty bits of mass, and converted them into energy. But it didn't matter how small the mass was, because when you're dealing with numbers that big, everything becomes big. And it is revolutionized the world, because it also not only governs how, like, not only states that the universe has been the same amount of mass energy since all time, it also allows for satellites to be in the air. It explains why astronauts are 16 seconds younger when they come back down. It's got a whole host of actually close to everyday applications. Smoke detectors use it. Why? So there's a little bit of radioactive material inside of them, and that's what powers it. That's how it's able to go for 16, 20 years without worrying. Yeah, it's used all over the place. And there's a number of excellent books that have been written on the history of this equation. Not Einstein, the equation. Biography on equation. I'll find myself out. Anyways, yeah, it's mind-boggling, and the thing is, it's so simple. This is, what, 5 characters? And you've all heard of it. And it governs how the universe works. It's amazing. The only other one that comes close into, yeah, whatever. E to the I. You guys know what I is? The
Imaginary
yeah.
-1
Complex, yeah, square root of -1 pi.
equals -1.
It has everything. It's got the equal sign, showing that both of the equation equals. It's got addition, it's got exponentiation, it's got multiplication. And it's got 3 random constants. Like, I wouldn't be able to come with these, like, if you paid me. And it all just works itself out and becomes 0. It's beautiful. Oh, I can't have this, but I get way excited about it. Alright, next. Oh, sorry.
Oh, wait,
Going the wrong way.
Oh.
Yeah, quantum. Alright, guys. I'll see if I can break this down. But honestly, I don't understand quantum mechanics very well. And really, neither do most of the people who've ever dealt with it. But what we do know about quantum mechanics is how to use it and abuse it. There's some really, really fun, sort of unintuitive things that you can use by exploiting quantum mechanics. So we're going to talk about quantum physics, the Higgs boson, and I'll touch on quantum field theory, but we won't go into it. Next. Yeah, quantum mechanics is probability-based. It deals with things at or around the size of an atom or an electron. And at that point, wave functions of things really begin to matter. Everything in this room, every person, every pen, pencil, object, has a wave function based on its mass. But that wave function at our scale is so small it doesn't matter. You aren't going to be entering 2 lectures at once anytime soon. It's useful in chemistry, and feel sorry for the chemists who have to use this because, God, it's so unintuitive. So sorry.
Oh, it's even worse with the chemistry lecturers. I don't know, I just remember dying.
It's my friend's dad.
Alright, now we'll go on to some of the unintuitive properties of quantum mechanics. Next.
Yeah, the delta equals.
Yeah, basically. So, double slit experiment. How many of you guys have heard of this? Alright, so I'm going to explain what happens for those of you who don't, or who haven't heard of it. So imagine you've got 2 holes in a wall, and you fire a gun at it. And this wall is made of steel, so it's not going to puncture the wall, it's just going to go through the hole. You're probably going to get a lineup that looks something like this in this styrofoam vacuum that you have. It's going to be clustered around directly in front of this sort of wall here. Now, if you do it again with waves, I've got a light here, but works equally well with light. If you put 2 waves, or sorry, if you send a wave through 2 slits in the wall, they're going to amplify and cancel each other out, and they're going to create a pattern that looks like this. Because these portions are the ones where you have small wave, and as they approach each other, they create a big wave. And then these ones are where you've got a small wave and a dip in a wave, and they meet each other and they cancel out. And so these black spots are where waves canceled, and these bright spots are where waves make bigger waves. Yes? This happens like every day in harbors and stuff. It's natural. And then you do this with electrons. Electrons, the way, how many of you have seen this? I'm running out of room, oh my god. How many of you guys have seen this model of an electron?
I know it's wrong.
Yes.
They're all wrong.
Yes, even more correct. This assumes that an electron is a particle, and it also assumes that this is a roughly equivalent distance. It's not. If the nucleus was this big, the electron would be like Hancock. Yes. scale is really weird. I should do a whole talk on that one. But, no. It assumes that the electron is a particle. It's not a particle, but the electron is a wave function. It exists as a probability. Where it's likely to be. But the funny thing is, when you send these electrons at this double slit, some of the if you don't watch it, if you set the machine going that shoots the electron at the wall, and it lights up when it hits, and doesn't light up when it doesn't hit, I guess. And then you leave the room and go have a coffee, go have a drink, whatever, come back the next day. You get a wave, which means that somehow the electrons were going through both slits and interfering with themselves. Yeah. They all the people who discovered this had a similar reaction. They're like, oh god, what happened? But because they're scientists, they're like, okay, we got this, we can figure this out. We're gonna watch how these electrons go through both slits. And so they set the camera next to one slit, and it ticked whenever the electron went through it, and it didn't tick whenever the electron went through the other one. And so they came back, they put the experiment going, went, had a drink, had a nap, whatever, came back, this one. It lined up like they'd been shooting bolts through it. Their heads, I can't imagine being in the room. What is this? This is because one of the properties of quantum mechanics. This is because one of the properties of quantum mechanics is that if you observe something, it changes the outcome. Simply by looking at it, simply by measuring it, you're going to change the outcome of the experiment. And there's a series of really fascinating information theory equations that I don't know off the top of my head that basically says you can only ever know so much about electrons. And in observing it, you're taking away some of the information, and you're forcing it to assume one or the other. You're taking away options from the electron, and it's forced to choose. I really don't like that word because it implies electrons and yes. And so this, again, revolutionary, changed our view of the world, and it leads to some really interesting discussions about free will. Because, sorry, I'm going to go on a bit of a tangent here. For a while there was a very deterministic view of the universe, which stated that if you know everything about a system, then you will be able to predict what happens. And this held true for a long time. Until you come to quantum mechanics, when you realize there's only so much you can know about a system, and everything that you don't know is inherently random. And so people thought that if you were to measure all the brain waves in a person, measure all their everything that was being input by the brain, you'd be able to predict what they would be able to do. This kind of just punches that in the face and says, no, you can't, because there's always going to be things that you don't know. Which means that if you measure everything that a human is achieving, measuring all their brain waves, you still won't know what's going to happen. You still won't be able to predict what they're going to do. You'll be able to say what they might do, what they probably will do, but you can't say with 100% certainty anything. This is have you guys heard of Schrodinger's cat? Yeah?
Yep.
Mm-hmm.
It was postulated by some guy named Schrodinger, who looked at this double slit experiment. He's like, dude, no way. Basically an actual quote. And he came up with this thought experiment to show why it was so ridiculous. And a lot of times it's used as an actual example of quantum mechanics when it's actually kind of saying no, you can't actually have this, because quantum mechanics only happens at very, very small levels. Schrodinger's cat says you've got a cat in a box and you've got a 50% chance of the cat dying, and until you open the box, the cat will be both dead and alive. And in practice, you can't do that because there's so many things affecting this cat, so many things that are measuring it, like bouncing off the cat, determining whether or not it's dead or alive, that if you tried to set this up in real life, it would fail. It would have a 50% chance of dying and a 50% chance of living, but it would never be in the same state at the same time, like the electrons going through both.
It also wouldn't get ethics approval.
Yep.
Yeah, killing a cat for one of these.
Plus, have you ever tried to get a cat in a box?
That was a hate. Thanks, God, actually.
Yeah. Next. Quantum tunneling. Just another example of an unintuitive property. I'm not sure how well you guys can you guys see this faint white spot moving across?
Yeah.
Okay. So remember I said that there was that an electron exists as a probability function? I'm going to draw the probability function for you. I think that's a Maxwell-Boltzmann curve. Yeah. Is that the name of it?
Mm-hmm.
Yeah. Which states that an electron has probability, it's likely to be here, but 1 in 1,000 times it'll be here, 1 in a million times it'll be here, 1 in 10 million times it'll be here. And if you send a whole pile of electrons, like billions of them, at a seemingly impassable barrier, you're going to get them, and they're going to come up against the barrier, and you're going to have the barrier be like here in this electron's existence as a probability curve. And so most of them will not, and they'll just bounce back, come back. But 1 in 1,000, 1 in 10 million, 1 in 100 million times, the electron back, I'm more likely to be over here. And it'll go through the barrier. And that is quantum tunneling. Because it's due to the very confusing and annoying nature of electrons' existence that they can actually be in all of these places at once, and until they're observed, they won't choose. Higgs boson. You guys heard about this? Probably. You've been living under a rock. Yeah. In, I think it was July of last year, July of 2012 maybe, they confirmed its existence. And it was peer reviewed and determined that yes, they actually had found the Higgs boson. So now Peter Higgs is famous and has one of the most significant particles in the universe named after him. Go Peter. Why do we care? The Higgs boson itself isn't actually that important, but what it implies is it implies the Higgs field. And the Higgs field is like it's like a giant thing of molasses. It's my best analogy, forgive me. And if you were to try and scoop your hand through molasses, you would slow down, yes? That's what this does to particles. It gives them mass. Because when these particles, which are seemingly massless initially, move through the Higgs field, they get slowed down, and some of their energy is turned into mass. And this mass is a direct result of Higgs field, and yeah, that's really all we know about it. There's a lot of stuff we don't know, and particle physics is particularly bad about not knowing things. Not only because of this, but also because of the enormous amount of money, effort, and time required to do it. Because you've got the Large Hadron Collider, which is one of the coolest things ever, and it was running for 30 years before they managed to find one of these. And there are so many more particles out there that we think should exist. Gravitron. We don't know which particle causes gravity. We know where it should be, like in terms of mass and size and behavior, but we haven't observed it. And kind of praying that it's out there, doing its thing, making gravity work. But the thing is, we can, because we're so certain of the way that these particles behave, we're confident enough that we can use the perceived properties and then base other things on these perceived properties. Which is why string theory is such a touchy subject, because it basically says the universe consists of a whole bunch of n-dimensional strings, and these strings give rise to particles, which give rise to more particles, which give rise to mass. We don't know these strings are there, and if for some reason something were to come out and say, nah, these strings aren't there, we kind of have to build from the ground up. It would just, like, shit all over Newton. It would suck. Next. Oh yeah, the Dirac equation. Paul Dirac was a funny fellow. He didn't really handle people well. There's actually a thing called the Dirac number, which is basically the fewest number of words you can contribute to a conversation and still actually be counted as having participated.
Wow.
And he was famous because he would sit there like surrounded by his physicist colleagues at like dinner parties or like tea times or whatever, and he'd sit there and then come up with the shortest possible sentence that he could contribute to the conversation and leave. That's how this guy rolled. But this Dirac equation is another, not famous, but incredibly important because it proves the existence of antimatter. It says that for every particle that exists in the universe, there's going to be another one that doesn't exist, or it exists as its polar opposite. And it immediately, antimatter is the opposite of matter. So you know how you've got charges with positive and negative? All of the matter in the universe is positive, and it says that there has to be negative matter out there. And it also elaborates the universal symmetry through this and through the behavior of various other particles. Works. It's up, down, top, bottom, term, strange, are the 6 kinds of works, and they come in flavors, and this guy said that, yeah, they're up there. Next slide is the Dirac equation, and I'm so sorry.
Hang on, aren't a lot of the figures
No,
in that
math.
sub-equations anyway?
Yep. It's, as I mentioned, it was horrifically complicated, and I am nowhere near proficient enough to explain it to you. But there it is, and this is important. Next slide. We're done.
I think that
Get
the
away from
W
me.
represents a whole other horrible, long, complicated equation.
Yeah.
The waypointers.
Yeah.
I know, first, like, chemistry
No,
lecture.
Hannah sounded like she was slightly confused.
Oh, right. The thing that looks like a trident?
Yeah, that. Well, it looks quite fancy.
It's
So,
not.
as I kind of bring this to a conclusion, I'd like to raise a point brought to my attention by Mr. Feynman in one of his lectures. If you think you understand quantum mechanics, you don't, because nobody understands it. Even the guys out there who created it, who performed the double slit experiment, they're like, how does this happen? If someone's telling you that they understand quantum mechanics, you slap them in the face and call them a liar. They don't.
Will do. This will hold up in court against the podcast.
Yeah.
Depends. We try to a physicist.
Yeah. So I don't understand very well, and I'm sorry that I can't explain it to you very well because my understanding of it is not amazing. But you know, then again, the people who invented it don't understand it, so I'm in good company. It's great. And then Randall from XKCD contributes this. It's true. The most complicated thing, or the most complicated phrase in the sentence is quantum mechanics, according to quantum mechanics. It's bullshit. Don't worry about it. It doesn't have any effect on you. Yeah. Thank you guys. I really enjoyed giving this talk, and it's fun getting to talk about something that I love, even if my siblings sometimes shut me up about it too soon.
walk through that wall if you go slow enough that it takes that long? How does that not have an effect on us? That's right.
Big infuriating there.
No, of course.
Oh no, according to quantum mechanics.
That
I know in the physics lecture and they say according to quantum mechanics.
And you just treat it like computer code in which the session asks me this bit does not count the
Some of
other.
the best resources for just physics in general, if you're just looking to have fun with physics,
It's so good.
and so this is just fun, like, what if experiments, like, what if I threw a baseball at 9 inches at the speed of light?
I'll pop this one up on the XSAC
And there was
page.
like, what if I have a mole of moles?
Yeah, what
Yeah.
would happen?
Oh, that was nuts. And
They're
one of
destroying the garden is what?
Oh,
Let's do
wow.
more than that.
And one of my personal, like, this is when I'm looking up subjects on, like, I go on one of those Wikipedia rampages and I have 35 different tabs open. And I realize I understand basically none of them. It's Wikipedia explained or written in very simple language, like third and fourth grade language. And I honestly find this site more helpful for understanding physics concepts than the actual Wikipedia. The actual Wikipedia is written by actual physicists who assume that everyone's as smart as them. This is written in terms that you and I can understand. Excellent.
Another one like that is Reddit.
Oh, yeah.
It's explained like on 5, so reddit.com/r/eli5.
If you're really lucky, 4chan is also good with physics, surprisingly.
Yeah,
If you dare go there.
If you dare go into.
And if you just want to
Like bullshit.
Yeah.
It depends on their mood.
Anyway, any questions?
Yeah, questions?
I think my brain hurts.
It does too.
So can you explain the Maxwell equations? Because they looked cool.
I can give it a shot. Yes, one.
Also, E to the MC squared
Both of them?
derives from the fact that they had equations for momentum for masses, and they also had it for light. And then they did some math privileges where they can basically put in the I just did the thing.
Yeah,
Roughly that. Essentially, where was it? The momentum for light is basically energy divided by the speed of light, and the momentum for mass, or for like a normal object, is